Hello and welcome to this presentation about the algorithm that we developed for automated teeth segmentation on 3D scans. Several methods exist for 3D surface analysis. The technique that was chosen for this work is a multi-view approach. This consists in generating 2D images of the 3D surface from different viewpoints. The generated images serve as a training set for a neural network. Let's dive into the architecture of the algorithm. First, we read the 3D surface, apply random rotations, and extract point features. Then we capture 2D views of the objects. The viewpoints are located on a icosahedron that surrounds the surface. During the rendering, we create a depth map and use it as a feature of the image. Rendering is done with PyTorch 3D, which is a library for deep learning that's specialized in 3D data. The PyTorch 3D rendering engine provides a map that relates pixels in the image to faces in the mesh and allows rapid extraction of point data, for example normals, curvature, labels, etc. After rendering is done, the images serve as inputs for a 2D unit. After inference, the information has to be put back from the images to the 3D surface. Teeth segmentation is a tricky task. Many difficulties have to be addressed. Some of them are listed here. So first, a lot of cases show missing or misaligned teeth. We all have different teeth alignments. Also, we don't all have the same number of teeth, so the algorithm must adapt to that. Some models have a large base, as you can see on this figure, and some don't, so the images that are generated can look very different. Also, there are some cases of teeth braces in the training set, which can alter the shape of the models. Finally, training a model on 34 different classes takes a lot of time, so some optimization must be made. For example, on the size of the images. We found that 320 pixels was a good compromise. To address those difficulties, we've come up with some additions to the code that make the algorithm more robust. First, we've added a random teeth removal step in the data loader. It helps the tool adapt to varying numbers of teeth and serves as data augmentation. Addition of class weights and making sure to have an even distribution of models with large base and others is an essential step to prevent overfitting to some cases. For example, there are usually less samples of jaws with wisdom teeth. It's important that during training the network sees roughly the same amount of cases with wisdom teeth and cases without. So for the training, we're using a MICCAI unit. So MICCAI is a open source PyTorch based framework for deep learning in healthcare imaging. It provides a complete framework to easily create datasets and integrate neural networks such as unit. So for the loss function, we're using the MICCAI's dice CE loss. It's the weighted sum of the dice and the cross entropy loss. We're using Adam optimizer and around 1000 scans are used for training. During the training, we're using the early stopping criteria to stop the training when the validation loss has stopped decreasing. So now let's see how the prediction is done. Multiple views of the models are taken. 35 to 45 views is generally enough to generate an accurate prediction. As you can see on the graph on the right, the position of the cameras are distributed on the surface of a sphere and follow a Fibonacci lattice to get an even distribution of the points. Then we apply the softmax function to the outputs and proceed to a majority voting among all views for each point on the surface. There are two post-processing steps. The first one is an island removal step. There are some spots that were not labeled during prediction, and this step gives the label of the neighbors to the spots that were not labeled. The second step is a closing operation that gives a smoother border with the comb. As you may know, ranking is based on three metrics that are teeth localization accuracy, teeth identification rates, and teeth segmentation accuracy. The first one computes the distance between the center of the ground truth and the center of the output for each tooth. The second one is the percentage of true identification cases, and the last one is the average F1 score over all instances of teeth point clouds. Our algorithm got 0.92 for teeth identification rate, 0.93 for teeth segmentation accuracy, and 0.99 for teeth localization accuracy, which gives a global score of 0.948 that ranks us in second place for the challenge. Comparing our results to those of the top 5 teams, we can see that the teeth localization accuracy is good in our case, and the teeth identification rate is excellent as well, but we may still want to work on improving the teeth segmentation accuracy, and one way of achieving better results would be to keep working on post-processing. We think that this algorithm is promising as it is an architecture that doesn't require any downsampling and that can be used for a wide range of surface analysis works. For example, we kept this architecture for the SLCN challenge, where the task is the prediction of gestational age at birth, and the input is a scan of the surface of a brain of a neonate. And we achieved very convincing results and ranked second on this challenge as well. Thanks for watching.